Hello and welcome to all our beta testers or potential beta testers also. I wanted to show you a little bit of our new MATLAB analysis system, which will be coming out soon. And if you signed up for it, you will get to take for a spin a little bit. And essentially, it's a system that's mostly command line based, so you can script in it, interaction only where needed. And it's actually a fully fledged atom probe analysis suite. For the first bit, you will get mostly data analysis tools, but in the next release, we'll also give you full reconstruction tools and even instrument calibration tools. So if you wish to build an instrument from scratch, we will also have that covered. Or you want to do your own calibrations on your current instrument. And so the whole thing works essentially by making use of innovations in MATLAB in the last 5 years, where the graphic system has been completely overhauled, and also where where tables have been introduced, which give an extremely advantageous situation for analysis atom probe data. So how does the whole thing work? Well, we have some ground truths and we have some data. And so let's start with the ground truths. And the ground truths, as we call them, are first of all our isotope table. So our isotope table is just simply, as it says, the table of isotopes with their abundances. And we'll give you one with natural abundances, but you might have reasons to change those if you do isotopic experiments. The simplest isotopic experiment is you have an FEI fib and you only have one gallium isotope, yeah, things like that. The second thing that we have is we have a color scheme, okay? And we will give you good color schemes for bright and dark backgrounds. And essentially a color scheme is just coloring for ions and elements. And you can have your own custom color scheme for a certain project, which makes sense if you have in one project colors that fit very well, but in another project you'd have elements that overlap if you use the same color scheme, so you can have a custom color scheme. And those are the most common ones. And the third ground truth that we need is our ion table. And sorry, there's still one little bug in there. It's just a visualization bug that you'll see running. But essentially, our third ground truth is a table of potential ions. And so right now, this is a just synthetically created table that includes the entire periodic table and carbon, nitrogen, oxygen. Yeah, this is the bug. For some reason, it has a problem with dysprosium. So if you're working on dysprosium, which we are currently, by the way, then this will show up, but it's not actually a problem. I don't know why it plots it out. Anyway, we'll have that fixed. And what the ion table is a table of potential ions. So for now, this is synthetically created. But we will have curated ones. So essentially, I have a student currently going through all atom probe literature and just finding which ions people have found in the past. And you may add to the ion table. And if you then want to load in your data, you can go post to table. It's now called post to table with TO and not to. It's not that important. I'll just load a data set from a steel in so that the mass spectrum is not too complicated. But our system has been extremely helpful working with really complex mass spectrum. We've been doing some geology recently. It's worth its weight in gold. Anyway, and then we want to have a mass spectrum. And the mass spectrum is plot mass spectrum. And what we need for that is we need our pos variable, and we need a bin size, and let's take a bin size of 0.01 Dalton, and we want to have it normalized. So we can have it in raw count or we can have it in normalized. And our actual analysis of the mass spectrum is based on the figure, on the actual MATLAB figures, okay? And so what we can do in the figures is actually we can place our ranges and we can place our ions. So in the end, when we actually do calculation concentrations, we can take abundances and the like into account and not just ranges, okay? And to do that, we can just go, in this case, ion add, and into our spectrum. And sorry, I'll just copy the ion add in so that I don't forget all the different things that I need to use. But usually this is now just to show you, usually obviously we heavily make use of autocomplete. So the ion that I wanna do an entry for is iron, and the charge state, you can have multiple charge states, but then the heights are not represented, of course. The charge state we want now is 2. We want to have our isotope table, we want to have our color scheme, that's fine. We want to have a sum margin of 0. So if you have a lot of isotopic possible combinations and there's just some that are very close to each other, you can merge them. The minimum abundance will also be 0, so that we also use the small peaks. The maximum height is taken from most, I think I called it most, let's have a look into this script. Max height is most abundant. Sorry, I'll just copy it in. So this will just take the height from the most abundant element. And the maximum separation is just for the peak search algorithms, so that's 0.1 usually is fine for well-calibrated mass spectrum, and we will have our ion popping up here. So this is if you already know what ions you have in there. If you don't know what ions you have in there, you can also do a search function, and a search function is find ion. Again, they will be a little bit renamed, okay? And find ion in the mass spectrum based on our ion table. And I hope I put that all in correctly. Not enough input arguments, so we'll have a look where I forgot to input something. Sorry, I know I shouldn't know my code, but usually I use autocomplete a lot. So ion table, isotope table, color scheme. Yeah. Okay, I'll just copy it from here. That makes it a whole lot easier. So if anyone ever asks you, it's your code, you should know exactly what everything is. No, I don't. Anyway, so we have our ion table that we have here. Then we've got our isotope table, so that the isotopic abundances are correctly reproduced. We use our color scheme. And we use a search range of maybe 1 Dalton. If it's not within 1 Dalton, it's probably not the right thing anyway. And then what we can do is we can mark a peak, like this peak here, and we'll get an auto suggestion and a pop-up box of what it could be. And silicon is probably a pretty good estimate, but I can go around and just go up and down, and it will, it will show me where the other peaks for my suggestions should be. But for now, I should be happy with silicon, and well, I know a couple of other things that are obviously in there. So there's going to be carbon in there. There's going to be carbon 2 in there. Carbon 2 1+, of course, in this case. I think that's just for showing stuff right now. That's enough. Probably I should also put manganese in. Manganese would be 2+. And now I've got my ions marked in the mass spectrum. And if I switch on the legend, then you will see that you can see which one's which. and the more dashed, the more solid the line is, the higher the charge state, essentially. If you click on the individual ions, it will just spit out which one it is, so they don't always have to just look at the don't always have to switch on the legend. The next thing is, of course, we want to add a range, which we do by add range. And in order to add a range, we just need to specify the mass spectrum we want to add it to, in case you have more than one, and the color scheme we want to use for that. So all I need to do then is go in and just mark my range, and it will automatically know what it is. So it's carbon 12. So we always take the isotopes into account, and I could just go for I equals 1 to 10, add range, so that we just add more than one range in one go. And I'm not going to zoom in for now, just because it's for demo purposes. And this gives you really the ability to range stuff fairly quickly. And I'll just mark some of the most important ranges, just because I don't want to, be talking to you for ages about minor element ranging. 10 is more than I thought. One more. Anyway, so now we've got our ranges, okay? And now I'll show you why the tables are so important. So if I now want to assign the whole thing to my range file, to my pos file, I can go pos, or I can call it, but usually I just write over the pos variable, because it just expands it, equals allocate range for this pos file, and we extract okay, was that already renamed? We had a little bit of a renaming going on. Ranges extract from mass spec. Thank you. Ranges extract from mass spec, and our mass spectrum is again the spectrum that we've done before. And what else do we need? Oh, and we want to decompose. Decompose means that our complex ions are being decomposed into individual atoms. And now if I open my pos file, you'll see, well, if you paid attention, it's gotten a little bit longer. And now you can see we've got our ion index, X, Y, Z, master charge. We see what ion it is, what charge state it is, what atom it is, what isotope it is, and what ion complexity it is. If you load in an EPOS file or data file from our OxCard atom probe, you get a couple of more things here related to, obviously, the experiment itself. Things like hit multiplicity and so on and so forth. So which pulse index everything comes from. And the reason why this is so great is because it really allows you to easily index into things. So for example, if I wanted to see all of our C2 ions, then I could go pos dot, and you have autocomplete now, so pos dot ion equals, oops, only 2, equals C2, and all entries for that. And maybe we'll just put that into some kind of variable. I'll just call it test for now. And now our test variable is all of our C2s, right? And in the C2s, you can already see that the ion is C2, but each one consists out of two atom entries from the same index. You can undecompose at any point when, if you like. But this is extremely powerful, and the reason why it's so powerful is because we are using categorical arrays. Okay, so here you can already see, if I click on any one of those, each of the entry types is a category, and you can index into those categories very, very easily. So you can build up very complex analysis with very little code. And I don't know where, okay, I think I just killed something during, while I wasn't supposed to. And for visualization, we can give you very nice visualization tools. So scatter plot from pos data. And here again, we'll have our pos. Then we'll can say which species we want. And this can be more than one species, by the way, and I'll show you just two. Okay, so maybe we'll want carbon, and we want manganese. Each of those, we want all of the things that are displayed, and I'll show you later why it's one means all of them, less than one means a fraction of them, more than one means a certain number of them. Then we want to have a color. We want to follow the color scheme, and we want to have a dot size of 1 MATLAB unit. And now, if we plot it, we'll get a figure that is rotationally linked. So you can see everything is rotationally linked, but each of those is a separate axis. And now with MATLAB 2019b, it's really, really easy to export your data. So you just drag it to whatever size you want. Then you click here, and you can copy it to clipboard as an image or as a vector graphic. And that is really the power here. You can export everything to a vector graphic very easily, which makes for really, really great illustrations. So on top of that, we also offer regions of interest. And just so that it doesn't get overcrowded, I'll just do that for carbon now and not the manganese anymore. Just so we don't run out of space, but obviously you can do that on a per whatever you like basis. And you can create a region of interest. And I will just create a box. And the box will be 20 by 20 by 20 nanometers. I don't know, you can make it whatever size you want. At the location, let's just put it at 0, 0, 0 in the current axis. And now we've created a box-shaped region of interest object, which we can programmatically move, or we can move it using the manipulate Roy interface. The manipulate Roy interface, which has no inputs. It's just a interface that it tell it, okay, I want to work on my object called ROI, because you could have more than one ROI. Now we've got it loaded in, and then you can start manipulating it. And after each manipulation, you can execute MATLAB code. So, for example, you can run a code that takes any atom of a certain kind that's within the box and display it somewhere else. So we use it to precisely align regions of interest, for example, with atomic layers. Yeah? It's very easy to do that way. Or you can use it, for example, to do chemical analysis or 1D concentration profiles or whatever you want inside the region of interest or in relation to the region of interest. We also have work coordinate systems, so you can also do it in relation to a work coordinate system. And then you can just move it. In this case, I'll just make 10 nanometer steps so that you can see that very easily. And you can pitch and roll. And this is always in relation to your current view, okay? So in relation to your current view vector, the way that you look onto the atom probe data, which makes it also much easier to align stuff. All of our analysis objects are really easily explorable. So if you go and look, for example, here into the mass spectrum, then and you want to, for example, delete a range, all you need to do is delete the MATLAB object. So for example, we want to delete the carbon-13 range. You just click on it and delete it, and it's gone. And the same with all of the other objects. So they exist as MATLAB objects, which makes everything very lightweight and easy to maintain. Anything atom probe specific is stored in the user data. So if I, for example, go into this carbon-12 range, and I've marked it now, I've clicked on it, then I can go, the object that I want to look at now is our current object. So GCO stands for get current object. And then I can go o.userData dot, what do we have? We have a charge state, we have hit multiplicities. It's defined on, in this case, it's defined on all hit multiplicities. We have an ion and we have the plot type. So the plot type is just to find out which thing is a range, which thing is something else. Most important thing for us is, of course, it's what kind of ion it is, and you can see there's a table as well. It's a C12 ion. Similar things are possible for the ROI. So I can click on the ROI object. Okay, clicking is maybe a little bit difficult right now because it's somewhere hidden in the middle of everything. But I can go ROI.userData. This thing has only 3 types of information: x-axis, y-axis, and z-axis. And we can use those axes for analysis purposes. Okay, so this is actually the basics. You can try that out already if you go into Atom Probe code. And in about 2 weeks, we'll have everything consolidated and migrated, and then we can give you a full rundown on the entire power of the analysis system. So I think it's gotten really slick, and it's most of all gotten really powerful in terms of getting you from your data to something publishable really fast, because everything is a vector graphic, everything can be scripted, and everything can be repeated for a lot of data sets very, very quickly. Okay, with that, I hope you're gonna have a lot of interest in what we're doing with this thing, and wanna contribute and wanna use it. So with that, we'll do the big rollout then in about 2 weeks.